Gracias. You want your laptop?
Your laptop?
Donations assigned. This on your right side. Just on the lapel itself.
Yeah, okay.
Okay, great. So our next talk will be by Panagiota and talking about combining and aggregating for fast synchronization.
Okay, hello. I am Panagiota Fatourou. I am a professor at the University of Crete and at the Foundation for Research and Technology in Greece. And today I'm going to talk to you about how to achieve fast synchronization. And I'm going to present basically two techniques, combining and aggregation. So I'm going to start with the basic stuff. We have an application, we want to parallelize it, and ideally we would like to be able to split the work into as many parts as the number of threads, and then execute all these parts in an embarrassingly parallel way. That would result in optimal speedup. However, we are in a real world. We are not in an ideal world. And we all know that the applications, most of the applications have sections, usually they are small sections of code, that should be executed in mutual exclusion, which means that no two threads can execute these sections at the same time. And this is what I'm going to call synchronization requests. And these synchronization requests can be either accesses of shared variables or accesses of shared hardware resources. And schematically, these are the colored circles here. So when it comes to accesses of shared variables, I can give you a lot of examples of shared variables, when we access the top pointer in a dynamic concurrent stack. The shared variable can be the first or the last pointer in a dynamic concurrent queue. It can be a field of a node in a concurrent implementation of a list, a tree, a priority queue, a hash table, or some other concurrent data structure. Or it can be a database object in a concurrent database setting. Okay, so I want to talk a little bit about the cost of synchronization. And here is a common belief that the best time to execute M synchronization requests is no less than the time required by a single thread to execute them sequentially, sidestepping the synchronization protocol. And this is so because of this mutual exclusion constraint that we have to impose, right? So now, in an ideal synchronization protocol, one thread would undertake the task to execute all the synchronization requests, and the rest of the threads would do nothing, so that I don't pay. However, in practice, the ideal behavior is never achieved because the threads have to run what is known as a synchronization protocol to impose an order in which the synchronization request will be executed, or to choose this one thread that would undertake the task to execute all the synchronization requests, right? And the fact that we're not going to stop writing parallel algorithms just because there are sections, small sections, that the threads need to synchronize, because other parts can be executed concurrently and give speed up. But what we have to do is we have to come up with synchronization protocols that have low cost, and therefore the cost of synchronization that we pay is not that big when the execution arrives at these code segments. Okay, so I guess you have understood already that my model is an asynchronous shared memory system, the same as what Robert Arjon presented yesterday and others a couple of days ago. So I have threads, I have shared variables. The threads communicate with each other by accessing shared variables, and the accesses to these shared variables can be reads, writes, fetch and add, compare and swap, and other primitives that are provided in the instruction set of the machine. And I'm going to give you the details of these primitives when I will need them on the go, on the fly. And the correctness condition is linearizability, which, roughly speaking, ensures that in every execution alpha produced by an implementation, each operation op in alpha must appear as if it has been executed atomically at some point, which is called the linearization point in the operation's execution interval. Okay? So there are protocols out there that have been proposed in the past to simulate the ideal behavior. And these are what we call software combining algorithms. The software combining algorithms, what they do, the threads first announce their synchronization requests by, for example, by writing a function pointer in a shared variable and possibly also the arguments to this function. And then they have to synchronize with one another to choose a combiner thread, which is going to serve, in addition to its own request, active requests by other threads. At each point in time, there exists at most one combiner, but it's not always the same thread as the time is progressing. And the rest of the threads that do not become combiners perform some kind of local spinning, and local spinning means that I'm gonna repeatedly evaluate a condition, and this condition has also tests the values of shared variables until the combiner informs them that it has performed their requests by changing the value of one of the shared variables, and then the condition evaluates to true, and these threads stop waiting. Okay? So here are some existing software combining algorithms. We have the most well-performed algorithms are CC-Sync and DSM-Sync that appeared in PPOP 2012. There is also in the same paper H-Sync, which works very well for non-uniform memory accesses architectures, and it's a general scheme. And the previous were flat combining, Koyama-Alg. There are also software combining trees. Now, software combining has been used to build concurrent data structures that are highly efficient, such as stacks, concurrent queues, concurrent dequeues, concurrent priority queues. And all these data structures have one thing in common. They have a small number of synchronization points, usually one or two, that might become a hotspot. And a hotspot is a point of high condension, is a point where all the threads try to access the same shared variable, right? And this can be top in the stack implementation, first or last in the queue implementation, etc., what I mentioned previously, right, in the previous slide. Okay, there is a downside. I don't know if it's a downside or a feature, because I don't know if it is unavoidable, right? No, it's not that I don't know, but I'm not going to tell you now. So I'm going to tell you later that in these software combining algorithms, there is no parallelism that is supported, right? There is nothing, and therefore they are not scalable. Okay, but this might be unavoidable because these are synchronization requests, which means access is to the same shared variable, right? The question I would like to answer here in this talk is, can we do better, even if all threads aim to access the same variable? And I'm gonna present a technique which is called aggregating funnels, and it is joint work with Yang-Han Ro, Wan-Hao Wei, Eric Rupert, Siddhartha Jayanti, and Julian Sun, and has appeared recently in PPOP 2025. So this technique answers this question. The answer is yes, but it depends on what kind of operations you have to apply on the shared variable, right? So it's not that you can do it for whatever operation, but depending on the operation, then you might be able to do something better. And I'm going to focus to fetch and add here. So because I'm going to focus to fetch and add, let me give you the semantics of fetch and add. It takes two parameters, a shared variable v and a value val, and it atomically adds val to variable v and returns v's previous value. It is a fundamental atomic instruction. It is widely used in concurrent computing, and therefore it is also available as a hardware primitive in most architectures. And recently, there is work that has proved that it is better to synchronize using fetch and add than compare and swap. And therefore, the recent effort, the last 10 years or so, or maybe 15 years, has been whenever you can synchronize using fetch and add, to use fetch and add and not compare and swap, because the cost of fetch and add, the hardware helps you, right? And the hardware does it fast, whereas in compare and swap, you have to repeatedly compare and swap, and this has cost. Okay, so just a small note about notation. I have implementations of fetch and add in software, and I'm going to use the notation FAA for the hardware instruction, and I'm going to use the notation fetch and add for the implementations in software. Okay? So fetch and add is very important. It has a lot of applications, a lot of concurrent algorithms are heavily based on fetch and add. Here are a few examples. We use fetch and add to allocate memory addresses for objects of varying size from a block of memory. For designing state-of-the-art universal constructions, and there are citations in the paper to all this, such algorithms that are based on fetch and add. They have been used, or the fetch and increment, which is weaker than fetch and add, to solve the readers-writers, a restricted version of fetch and add, to solve the readers-writers problem, to assign distinct IDs to threads or distinct timestamps or tickets to operations, in reference counting, when it comes to garbage collection, to implement simple barriers, to implement array-based queue locks, which are the state-of-the-art locks in concurrent computing, and to design highly efficient concurrent queues, stacks, and other data structures. And when it comes to concurrent queues, you may know that LCRQ is the state-of-the-art queue, and it is heavily based on fetch and add, and I'm going to explain later. Okay, so I hope I have persuaded you that fetch and add is an important primitive, and we would like to have fast fetch and add implementations. However, the hardware fetch and add, in the hardware fetch and add, there is a downside of the hardware implementation, which is that all concurrent fetch and add on the same memory location V are executed sequentially. And therefore, there is no parallelism, and this implementation, the hardware implementation, is not scalable. Okay, so in the aggregating funnels paper, we propose an implementation of a fetch and add object O in software that supports, of course, fetch and add, read, but also supports any other instruction in the instruction set of the architecture for accessing shared variables. So basically, we implement in software fetch and add this object, and to implement it, we use hardware instructions such as the hardware fetch and add and reads and writes. So basically, we use the hardware fetch and add to build a fetch and add in software, and we would like this software implementation of the fetch and add to be scalable. And we saw into the paper that our implementation efficiently mitigates contention and outperforms the hardware fetch and add up to 4 times. So we are much better than the hardware fetch and add. And also, we have used the proposed software implementation of fetch and add to improve LCRQ. So we have plugged it in, let's say, we have plugged it in the LCRQ implementation, and we saw that the variant we get outperforms the original version up to 2.5 times. Okay? So now I'm going to get into the main ideas. I'm going to use a shared variable, which is called total sum, and it always stores the actual value of the implemented object O. Okay? And the threads are going to execute hardware fetch and add on this variable, but I'm going to also use M structures that I call them aggregators. And what I'm going to do is I'm going to distribute the threads into these aggregators. And now, if I have P threads in the system, I'm going to have, and I distribute them evenly, then I'm going to have something like K, which is equal to P over M threads going to each aggregator. And these K threads now are going to compete in each aggregator to choose a combiner. And basically, this is a kind of a K-way combining scheme. And this way, each aggregator aggregates batches of fetch and add operations to reduce contention and increase parallelism. I'm going to give more details later on. The goal is to distribute the contention across the M aggregators, so the contention is now reduced from P, which was previously because all the P threads would go to the same shared variable and would perform the hardware fetch and add, for instance, to P over M. And P is the number of threads, M is the number of aggregators. And note that when M equals square root of P, the contention becomes also square root of P. And of course, you can tune your system so that to get nice trade-offs there, okay? And also, this scheme allows for increased degree of parallelism because the threads that go to different aggregators are going to compute partial sums, so they are going to compute the sum of the arguments of the fetch and add operations that they want to execute in the aggregator, and then the combiner is going to simply apply one fetch and add on total sum to apply all of these fetch and adds by adding the partial sum that is now already in the aggregator. Yeah, we can make it multi-level. Yeah, I'm gonna explain a little bit later, okay? So we didn't have to make it multi-level in the machine that we experimented because we made it, but we didn't get better performance. But if you go up to 500 threads or 1,000 threads, then you may have to make it multi-level to mitigate contention, right?
Missing something basic. Like if there is a fetch and add performed by a thread using aggregator 1 and a fetch and add using of a thread in aggregator M, how would they know about each other? Okay.
I'm gonna give many more details, and then if I don't answer your question, please ask me again. Okay? So that's the major ideas. Sorry, and the scheme reduces contention and increases parallelism. And this way, in a sense, we beat this common belief, right, for this specific framework, this specific setting where we want to implement fetch and add. Okay, so let me just say that to ensure correctness, we linearize an entire batch of operations at the batches hardware fetch and add on total sum. And the invariant we are going to ensure is that this total sum holds the value that the implemented object O would have if all operations linearized so far were performed on it. And therefore, this is a correct implementation. Okay. Now, this scheme may seem to be simple, but it's not so simple, and it has a lot of challenges that we need to address. One challenge is how to choose the combiner for each batch of operations. Another challenge is how to decide which operations will participate in the batch. And what is a batch now? Okay, the threads come and have a fetch and add, but when they finish, they are going to come again, right? So the combiner cannot wait forever. At some point, it has to close the currently. So the aggregator has a lot of batches of operations, and the combiner has at some point stopped waiting for threads to arrive, right? And it has to close this batch, the currently active batch, and initiate another batch so that if the threads come again, they are going to go to the next batch, right? And this way, we ensure progress, right?
I don't know what's important, but maybe. So is there a fixed mapping from the threads to the aggregators?
It's not important, but in our experiments, yes, we have a fixed mapping, but it's not important. The threads may start by choosing which aggregator they would like to go, and in the future, in the open problems, you will see that coming up with some kind of adaptive scheme might be a good, direction to do more research. Okay. But it's not important. It's just that this is what we do in the experiments. So we have, each aggregator has a lot of batches, and we have to decide which operations will participate in the batch of each aggregator. And also, and this is the most difficult challenge, is how to propagate the return values to the waiting threads, right? Is this clear? Any question up until now? And now I'm going to get into these challenges and explain how exactly the algorithm works. Let me zoom in in an aggregator right now. I give you more details about what is an aggregator. An aggregator is a struct that has two fields, agsum, which stores this agsum field stores the sum of the arguments of all the fetch and add operations applied to the aggregator thus far from all batches. Okay? And the batch is a pointer to the currently active batch. Is this clear up to now, the scheme? Okay. And we also have this total sum. So this is how the whole thing looks like. And again, notation, the shared variables names are capitalized, whereas the thread local variables names are not. Just keep this in mind. It might help you to follow. So here is a high-level description of the algorithm. A thread first chooses an aggregator ag, and then performs a hardware fetch and add on its agsum field, and this acts as an announcement of the fetch and add to this aggregator. The combiner of a batch B is going to be the thread that performs the first hardware fetch and add on agsum after B has become the active batch of this aggregator. All the other threads than the combiner perform local spinning, waiting for the combiner to signal them. When this happens, when the combiner indeed signals them, the operations that belong to this batch know that their requests have been served and they can calculate their response and return. And there are some other operations that are not assigned to B, that do not belong to B, and they also wait for the combiner, and those operations will be redirected to the most recent active batch of the aggregator to attempt to accomplish the execution of their operations. Okay, this is the high-level description. And now I'm going to get into, I'm going to give you a little bit more details. So I'm going to first answer the question, how does an operation figure out that it was the first in its batch to execute a hardware fetch and add on agsum, and therefore it has to act as the combiner? What I'm going to do is I'm going to have one field in the batch, in each batch, which is called after, and stores the value that the agsum had after the operations of the previous batch to B were applied to agsum. Right? This is exactly the value that the first fetch and add on agsum by the operations on B will return. Right? Do you understand this? Is this clear to everybody? Yeah. Okay. So.
May not be the only time you see that value. You can have negative adds.
If I have negative arguments, you mean?
Yeah.
I support negative arguments, but here I focus on positive arguments. So I'm going to answer your question at the end of the presentation. Okay? So here all the arguments are positive in this scheme. Okay, very good question. Now let's assume that the thread T1 arrives and wants to execute a fetch and add. And for simplicity, I'm going to assume that all the arguments are equal to 1. So this is more or less a fetch and increment. It's not a fetch and add, but a restricted version of fetch and add, I mean. And then what is going to happen is that this thread is going to perform a fetch and add on agsum. It's going to see 0, and it's going to change its value to 1. And it's going to save the 0 that it read in agsum in a local thread variable which is called before. Okay? And then let's assume that another thread comes. It's going to also perform its fetch and add. It's going to see 1 and change the value of agsum to 2. And a third thread is going to see 2, and it's going to change the value of agsum to 3. Okay? So here is where we are now. Now, the combiner, which is this guy here, decides that it is the combiner because it compares the value in its local variable before with the after field of the batch, and because these two values are the same, it decides I was the first to perform the hardware fetch and add, and therefore I should act as the combiner. Is this clear? Okay. Now, the other people, the other threads that are there, T2 and T3, are going to compare are going to do the same. They are going to compare their before values, which are 1 and 2, with 0, and they will decide, okay, we have higher values, we were not the first, we're not going to act as a combiner. Okay? And what we're going to do is we're going to perform spinning. So we're going to repeatedly read this batch after until we see there a value that is larger than 0. And then this is going to be the signal that the combiner gave us to stop waiting. Okay? Good. So how does the combiner act? The combiner, after possibly backing off for a small amount of time, does the following. It performs a read R on AgSum, reading some value V, now our example 3. And the operations that have performed their hardware fetch and add on AgSum between the combiner's hardware fetch and add on AgSum and R belong to B. So all these 3 operations, right, that I presented previously. And these 3 that the combiner read is going to be stored in a local variable after. And then it's going to perform a fetch and add to add the value after minus before to total sum, which is the partial sum of these 3 operations, right? So the total sum contains 3 after this, and the previous value 0 is going to be stored in a local variable T as before. And then it's going to allocate a new batch B prime. It's going to set the after field appropriately to 3 now, and then it's going to change ag batch to point from this batch from B to B prime. Now, okay, this is what the combiner is going to do. And now, how do threads understand that they should stop spinning? What they are going to do, remember that these 2 threads spin by reading the batch and then the after field. Now what they are going to do is that when they are going to read this after field, they are going to now be directed to B prime and not to B. They are going to see that there is a 3 there, and this 1 and 2 are now smaller than these 3, and therefore they will say, okay, I have to stop, and they are going to stop. Okay? Now, how does the combiner calculate its response? The combiner is going to be the first to be, it simply returns T as before. What it saw in the total sum when it executed the hardware fetch and add to add the partial sum in the total sum. And why is this correct? This is correct because the combiner is going to be linearized first out of this batch. And this batch is going to be linearized together, and the combiner is going to be the first, and therefore it has to report the value that it saw in the total sum before it applies any of these operations, right? And it applies them all together by a single hardware fetch and add. Okay, and how do the other threads calculate responses? This is more difficult, actually, and the difficulty comes from the fact that these 2 threads belong to B. But now the currently active batch is not B, is B prime. And therefore, the combiner should store into B prime appropriate information so that these 2 threads can find their responses. And the information is in B prime before, the combiner should store the value of AgSum before the operations that belong to B are applied to AgSum. For each thread, and then if this happens, for each thread Ti, the value before minus B prime before is the sum of the arguments of operations that belong to B, which have performed their hardware fetch and add on AgSum before Ti. And it also stores a field T as before, and the B prime T as before stores the value of the total sum before the combiner applies any of the operations that belong to B to total sum, and therefore these guys should return B prime T as before, which is the value in total sum before I start applying any of the operations of the batch B, plus this partial sum of operations that precede me in the linearization. right? Which is before minus b prime before now. But it doesn't matter. This is probably complicated. But this is how the scheme works, okay? And why it is correct. Let me now move on to the, there are other complications that I don't mention. Please read the paper if you want to find, somebody asked me about some of the details. I don't know if the details now have become more clear. I'm going to move on to the experimental analysis. Here you can see the implementation we propose. This is throughput, so higher is better. Here we can see the multi-layer aggregating funnels. Somebody asked me, I don't remember who. Oh, Jan. But it doesn't perform the same well. There are certain compromises here, right? If you have multiple levels, you have to apply hardware fetch and add in all these multiple levels, and you have to access more variables, right, than one if you are not the combiner and two if you are the combiner.
So ag funnels is just a two-level scheme, like with root P.
The experiments are with the two-level scheme, what I presented, right?
The operation will require, I guess, one fetch and add plus.
If one fetch and add if you are not the combiner, and if you are the combiner, two fetch and add, hardware fetch and add, right? Yes, okay. And then we also have combining funnels, which is the previous state-of-the-art software implementation. I'm going to talk a little bit about this later on, and the hardware fetch and add. And as you can see, we are much, much better than the hardware fetch and add. And also, here is the experiments. I don't have time to explain all the details of what we see in these experiments, but here you can also see that when we apply our scheme in LCRQ, which is this concurrent state-of-the-art Q implementation, we get much better speed up in this application as well. Okay? So, related work. Some of the ideas that I presented are not completely new. They were there in the past, in previous work. For instance, a technique for K-way combining was proposed by Tang and Yu in the Journal of Parallel and Distributed Computing in 1990. But it's a more complex scheme than our scheme and uses primitives not available on modern machines. There is a technique which is called combining trees for fetch and add that has been proposed in IEEE transactions for computers. It uses a complete tree of height theta log p, assigning a leaf to each of the p threads. And it employs combining at each node of the tree, but it has been criticized that its performance is sensitive to the arrival rate of operations because independently of the condension of how many threads you have, all threads have to go up the entire path of depth log p, and this is a lot of shared variables to access as you go. And there is also what is known as combining funnels by Sovit and Zemach, which has appeared in 2000. It tries to solve the problem of combining trees by replacing the static tree with a series of combining layers through which the fetch and add operations are supposed to pass. The combining funnels was the previous state-of-the-art technique. It has been experimentally shown to outperform all other previous approaches. But still, as our experiments show, they are significantly slower than the hardware fetch and add, whereas we are much better than the hardware fetch and add. And the reason is that these approaches considerably increase the number of variables that are accessed by software fetch and add, right? Okay, so conclusion, we proposed aggregating funnels, which is a software implementation of fetch and add that is much more scalable than hardware fetch and add and more efficient than state-of-the-art software implementations. The aggregating funnels support both positive and negative arguments in fetch and add. And to answer Phil's question, the way we actually support negative arguments is by having another set of M aggregators. And if you have a positive argument, you're going to use the first set of M aggregators, whereas if you have a negative argument, you're going to use the second set of aggregators. And then, we do some extra tricks to basically manage when you arrive at total sum. So basically, the aggregators use in the aggregators, we sum up the absolute value of the argument. So you don't sum and then negate or whatever. And the scheme is not optimal because when you have negative and positive arguments, you can probably eliminate in the aggregator, but we don't do this, okay, in the current scheme. So there is room for improvement. The construction can be applied recursively to reduce condension and get a multi-layer design. We can replace total sum by an instance of the proposed algorithm, and we can also replace the AgSum field by an instance of the algorithm. This might be beneficial when we go up to a higher number of threads. Aggregating funnels are strongly linearizable. We have a formal proof in the paper. They handle overflows in aggregators, but overflows in total sum behave the same as overflows that occur when we apply hardware fetch and add on total sum. They support high priority threads. They also support read, modify, write operations like compare and swap and any other such operation that is supported in the instruction set. And they don't support them very efficiently, but they do support them. And we have demonstrated that the speedups observed in micro benchmarks translate to higher level applications by deploying the proposed technique to LCRQ, yielding a significant speedup in the performance of the queue. Our code is available, widely, freely available. You can find more applications under this URL. Here are some future directions. We have applied our technique on fetch and add, but we believe that the same technique works for fetch and store, fetch and add, and other such primitives. But what about fetch and fee, where fee is some function, right? Which is a more general primitive, and there we may need some kind of characterization. So phi may have to have some properties in order for the scheme to be able to work. This is a very nice direction for future research. We would like to get a NUMA-aware implementation of aggregating funnels. We could go to some kind of an adaptive scheme, as I also answered the question previously, where the algorithm becomes self-tuned based on the architecture and on the workload. And also we would be interested to see whether this technique, this approach can be implemented in hardware and what would be the outcome in this case. So thank you very much. And before I close this presentation, I would like to tell you that I'm currently acting as the steering committee chair of PODC, and that many papers that are presented in the workshop, I believe, are very good candidates for PODC. And please consider to submit to PODC as well, not only to SPA. Thank you very much.
Yeah, I have two questions, actually. So obviously this is designed for like the high contention case, but what are the overheads when it just happens that there's only one thread trying to do a fetch and add?
Yeah, well, if you have just one thread, then the scheme is twice as expensive because this thread is going to be the combiner, and it's always going to be the combiner, and it's going to perform 2 fetch and adds instead of 1, right?
Okay. And I had a second question, which was, so you're assuming like no failures of threads or anything like that?
This is blocking, yes, it's blocking. So no failures. Other questions?
So actually, following up on Jeremy's questions, what is the overhead in the uncontended case? And can you say a little bit about like the space overhead? So if I want to create one of these objects, let's say I have an 8-byte variable, how much space do I need?
The space overhead comes from two places in the algorithm. One is that you use these batches, right? So every time you install a new batch, the previous batch can be reclaimed. So we use an EBR scheme to reclaim batches. And therefore, if we don't count how many batches have been reclaimed and have not yet been deallocated, then the space overhead is just order M, the number of aggregators, right? Because there is always just one, well, more or less. And now when it comes to this more complicated version of the algorithm that also handles overflows, there you have to assign aggregators as well, new aggregators if an aggregator overflow. And again, we can use EBR or other schemes to reclaim memory. And there are bounds in the paper.
And yeah, so what about the overhead for the uncontended case? Like I mean, the experiments were showing what happens in the highly contended case as we scale the number of threads, right? So what is the overhead you're paying for a fetch and add when there's no contention? I guess it's just too...
It is double, yes. If it's I answered previously, right? Yeah, that was the question. Yes, sorry, that was a question of Jeremy as well. Yes. I didn't repeat it, so yeah.
So I guess this is related, but one of the things that was tried in years past when, like, flat can mining, funnels, and all these things, was is there a way to attempt to go straight to the, the one fetch and add, and then if you discover contention, you back off and you do the...
Well, right now, we assume that if you are a high priority thread, you can go directly to total sum and don't do all this algorithm. And this is perfectly fine. We can linearize it, okay? Mm-hmm. But we don't have this adaptive scheme that you want. We don't have the mechanism to adapt. So if you can plug in the mechanism to adapt, then this scheme is going to work. But I don't have the mechanism to adapt to give to you. So yeah, this is a nice open problem. But this is how we actually execute this compare and swap and fetch and add by high priority, threads which have high priority, or get and set, or other primitives that the instruction set supports. This goes directly to total sum, and they screw up performance a little bit, but they are still linearizable if you do this. The scheme is still linearizable, right? So it supports it.
Questions? Great, thank you very much.
Thank you.
We'll continue at 9 tomorrow, and Kurt probably has something to say.
Yeah, so if you want to go to the botanical gardens now, why don't you just hang around? If you're not going to the botanical gardens, you can take off or whatever.
There should be tea on the second floor.
There's tea on the second floor and probably coffee.